Good day. The title of this presentation is Mid-Century Modern Masonry Cladding Systems, Experimentation in Detailing and Resulting Challenges. Learning objectives include gaining an understanding of the key differences between historic wall assemblies and mid-century modern wall assemblies, to provide an overview of various masonry cladding systems that were used in the time period between 1945 and 1970, to identify common distress conditions relative to various detailing and material issues that are unique to mid-century masonry-clad buildings, and to provide an overview of how lessons learned from the evaluation and repair of mid-century modern masonry-clad buildings have impacted post-1970s wall systems. An outline of this presentation will include a brief background, common masonry materials used during the period, detailing issues, material issues, and finally a few case studies. Here we have the four basic masonry wall systems that have existed over the last 150 years. Starting in 1870 and prior to that, solid masonry mass wall systems, transitional wall systems between 1870 and 1950, in which the structural system was integrated into the exterior wall. Mid-century modern walls where cladding became more pronounced and separated from the backup assembly and structural system. And then finally, modern traditional wall systems that are used today, which have become much more complex, incorporating weather barriers, air barriers, insulation, lateral anchorage, and various components in order to make the system function properly. Common masonry materials that were used in mid-century wall cladding systems include brick, glazed and face brick, concrete masonry units, often decorative, terracotta, cast stone as an imitative material for cut stone, stone face precast, thin stone, and finally glass block. Some common issues that exist in mid-century masonry cladding systems include lack of expansion and movement provisions, including horizontal expansion joints and vertical expansion joints, poor water management, including a lack of flashings, improperly installed flashings, poor flashing materials, and collar versus cavities, thermal, including insulation as well as thermal bridges, material issues, stone anchorage, hysteresis, strength loss, mortar compatibility, poor durability, corrosion of both gravity support and lateral support, as well as reinforcing, and then finally, construction tolerances. I'll go into each of these in a little bit more detail now. This slide shows two examples of inadequate expansion provisions. The image on the left is unaccommodated vertical expansion resulting in displacement, likely also contributed to by the lack or loss of lateral anchorage. And the image on the right is lack of horizontal expansion provisions resulting in cracking near corners at intersecting walls. Here are two more examples of unaccommodated expansion provisions. On the left, vertical expansion resulting in displacement, and on the right, horizontal expansion resulting in compression of joints and sealants within the vertical expansion joint. This particular detail shows a horizontal expansion joint as depicted in the Indiana Limestone Institute documents that were produced after World War II. What you can see is an attempt at creating a movement joint, understanding the differential movement between the limestone cladding and, in this particular instance, the concrete backup. Often these were not adequately designed or installed, and the materials used to them over time became brittle and thus not accommodating the expansion long term. This detail represents another means of accomplishing a horizontal expansion joint at a shelf angle location or at a floor line. And what you'll see in this instance is corrugated lead or lead sheet that was put in at areas where they wanted to accommodate vertical expansion through a compressible material. The problem with lead in this instance is once it's compressed, it doesn't have any elasticity and it doesn't rebound much like sealant would today. These are some details from Graphic Standards, which is a publication that's in the States, also following the war. And you can see some attempts, generally with sheet metal provisions, to accommodate movement while having those be bonded to the various cladding materials in an attempt to accommodate the movement within the system and keep the areas dry as well. Here are a few more examples of vertical expansion joints detailed during this time period where the metal flashings were intended to keep water out and accommodate movement. In all of these systems relative to accommodating vertical and horizontal expansion in the detailing, one of the issues that frequently exacerbated these situations was the use of corrodable metal used in these instances. As the metal corrodes, scale accumulates and occupies a volume often 4 to 10 times the volume of the uncorroded steel. When this is confined by rigid masonry materials, it can also result in distress and displacement as that scale accumulates and becomes more and more severe over time, until ultimately potentially dramatically impacting the structural capacity of the individual members or the assembly in general. Here's an example of lack of vertical expansion accommodations where a shelf angle is installed into a joint without a soft joint below. As the brick expands and corrosion accumulates and exacerbates the situation, the brick can begin to spall and displace from the building. This is a very common distress condition that's observed often in limestone cladding systems where the shelf angles, typically located at each floor line, corrode. It's confined with no room for the scale to accumulate, and the resulting distress is spalling in the outward face and in some instances on the inside face not visible of the limestone itself, and you can see that here. Another consideration in mid-century facade systems is accommodation of tolerances. Generally, particularly with masonry systems, the tolerances are much tighter than the structural system behind it, whether it's steel, concrete, or masonry itself. Those tolerances have to be accommodated in the detailing of the system. And while those were understood at some basic level during the early part of the mid-century, accommodating those and how that was accomplished was also done through some fairly extraordinary means in terms of field modifications made by the contractors. And you can see a couple of examples of those here. Here we see an example of 3 construction tolerance envelopes. The yellow areas depict variability that can exist within the system, whether it be steel in the left 2 images or concrete in the right image. And the cladding system on the outside, in order to be installed within very tight tolerances for masonry, has to be able to accommodate that through the anchorage assemblies, whether it be in and out or up and down within the assembly itself. Here we see an example of 2 instances in which tolerances were not properly accommodated, where the toe of the horizontal leg of the angle that supports the brickwork is too close to the outside face of the brick, resulting in either an exposed portion of the angle or a very thin, inadequate sealant joint at the toe. This is an example of stone anchorage in which the back face of the stone panel was notched in order to accommodate the horizontal leg of a shelf angle, which provided gravity support for the panel, and in some instances, if a tab was also attached to the leg of the angle, it provided lateral restraint. As you might imagine, this was a difficult detail to install properly in order to both support the gravity load as well as the lateral loads on the panel. One of the byproducts of the Second World War was significant advancement in sealant technologies. Prior to World War II, many of the sealants, or caulks as they were called, often had very little movement capabilities and became hard and brittle over time. Oil-based caulks generally had 2 to 5% movement capabilities. During the war, polysulfides were developed which had greater movement capabilities, but over time those became more brittle and were not functioning properly. Then there was the development of urethanes as well as silicones, urethanes being plastic, which had 25% movement capabilities and had a more limited service life than the silicones, which had greater movement capabilities, lasted much longer, but also had ramifications in terms of staining of porous masonry material. A key ingredient in many silicones are plasticizers. You see 2 images here of plasticizer migration. In both instances, these are silicone-based sealants where the plasticizers or oils from the sealant themselves are absorbed into the stone and changed the visual characteristics of it as well as the hydrophobic characteristics of the stone in the area where the plasticizers have migrated into the masonry itself. One of the common misconceptions during this time was that harder mortar was better mortar. And while the mortar technologies were advancing in order to develop masonry cements and other types of pre-bagged mixes, getting past this notion that harder mortar is better was critical to this time period and some of the issues that resulted from. As we've seen previously, during this time period, flashings were beginning to be introduced into the system because there was a greater understanding that there was more need for water management than had been the case with mass masonry wall assemblies. Flashing materials early in the period included copper, copper fabrics, copper composites, aluminum composites, and plastics. Here we see an example of nervostraw, which was very commonly used during this time period, which is plastic, and some details that were included in the literature provided by the flashing manufacturers. Here you see some examples of some of the advertising for flashing materials that were common during this time period. This is an example of flashing details that were used during this time period, in which the flashings, if you'll notice at the head of the window, extend down the vertical leg of the angle, but do not extend out past the horizontal leg and only slightly extend onto it, resulting in corrosion of the unprotected steel in these types of situations. Here are a couple other examples of flashings in wall systems, and you can see the flashing is not very well developed, often doesn't extend out to the face or daylighted, resulting in potential water not actually exiting the system as intended. One material that was being widely used during this time period was thin stone cladding systems. These really had not existed prior to World War II, with few exceptions, but stone, including marble and granite, and in some instances even limestone, were being cut to less than 2 inches and installed using entirely different assemblies and anchorage systems than had existed previously. In this particular instance, this is marble, and one of the phenomena of marble in thin applications is what is known as hysteresis, which is this bowing that you're seeing on these panels, which is a function of the metamorphic stone itself and its behavior as it weathers in thin applications. The previous slide had depicted bowing of the panels. In this instance, we have what's known as cupping, or inward displacement of the panel at the midpoint. One thing to note about hysteresis is that generally the greater the bow, the greater the loss of strength within the stone panels themselves. Thin stone applications of travertine were also commonly used. Architects were very fond of the material and its characteristics and inclusions that exist within it. The stone generally performs fairly well, but many of the inclusions result in problems when anchorage or associated anchorage of the panels themselves corrode, or as the panel is exposed over time and some of the natural veining of the material manifests itself ultimately into discontinuity or cracks. Here you see one of the tricky things with travertine panels, where you have natural inclusions which may have the appearance of distress or cracking versus actual distress or cracking that could result from embedded steel anchorage corroding over time. Another stone that was very popular during this period was serpentine, which is a very beautiful green metamorphic stone, but is also a very weak stone which has many veins and inclusions which result in discontinuities within the stone itself. In some instances, the backs of the stone were routed and rods were inserted to provide added strength, and you can imagine the resulting distress that resulted as those bars corroded. Much of the detailing of thin stone applications in this particular image, serpentine, was that stone detailing that had been used for the interior of buildings was used on the outside of buildings, and that was not generally a good idea because of the significantly higher loads and exposure that the stone was subjected to during those time periods. But that was a detail and detailing system that had existed for a number of years at that point. It just hadn't been moved to the outside in thinner stone application. Here you see some of the anchorage details that were used during this time period. One characteristic of these was they were typically interior details that were used or moved to the outside of the building in order to support the thin stone applications, because thin stone had been used more commonly on the interior buildings prior to being moved to the outside for some of the cladding systems of the mid-century. These are some more details for some of the applications where you have off-the-shelf lateral anchorage shown on the left, and then you have an installation application on the right. Another example of some of the stone anchorage used during this period, we have very thin limestone panels on the left two images, and then liner blocks that were used on the right image for added gravity support, as well as some mortar blobs that were used for inward load. The left shows two examples of mortar blobs used in the system, and the right actually shows one of the problems with these is that often gypsum was added to the mortar to enable it to set up faster, but as that gets wet over time, it is expansive, much like corrosion scale, and can result in fracturing of the stone. Another system that was popular was stone face precast panels, in which one or several stones were anchored to a concrete panel, and then those were lifted into place and installed. Terracotta was being used as a cladding material, but not to the same extent as it had been previously. Terracotta was also being touted as a facelift material, or a material that could be used to overclad older buildings that had a tired look or a perceived tired look that was no longer desirable during the 1950s and post-war era. And you can see some examples of that here in the advertisement that was used, where these very simple flat panels would be installed over the masonry in order to give the building a facelift. Now I'll quickly run through a few case studies to show some examples of the systems and issues that we've dealt with. The first case study is a building built in 1969, 4 stories tall in Toledo, Ohio, that has a reinforced concrete frame structural system and is clad with clay brick masonry. One of the defining features of this building are these large brick haunches that extend out from a cantilevered structural system and create one of the design features of the building. This is an excerpt from the structural drawings, and here you can see the fairly large cantilevered systems that extend out from the main building line that help support and provide structural support for the haunches, which are exhibiting the stress. This is an architectural detail of a section through the haunches that shows the structural support for the brick cladding system, as well as the concrete structural system behind the haunches that create the elements. This is the detail at the top of the building, showing how the brickwork is integrated into the structural system and the CMU backup in the flat wall sections. And these are the repairs that we developed, rebuilding the haunches that exhibited the cracking from a combination of corroding steel and inadequate structural support. We came back in with reinforcement in the cantilevered portion of it that was tied back in to the main body of the haunches to provide a lateral restraint for the cantilevering of the haunches. The next case study is a building constructed in 1965. 9 stories tall, located in Washington, D.C., also with a reinforced concrete structural frame and clad with clay brick masonry. The structure here was also a reinforced concrete frame with significant cantilevers, and you can see what happened shortly after construction, where this ziggurat configuration resulted from the formwork for the concrete pours and the cantilevers being pulled too early, and the cantilevers themselves relaxed and the brick went along for the ride, resulting in this ziggurat type configuration. These are some drawings from original construction. On the left is a structural section showing the cantilevered section within this area, 2-way structural slabs, and then some other detailing for supporting the masonry off of these slab systems. Rather than reclad the building, it was decided that the areas exhibiting the most outward displacement near the top of the building would be reconstructed plumb, and then the rest of the wall was left in place with the configuration as it had existed. This is another one of the repair details, the existing condition on the left and the repaired condition to bring the brick to plumb on the upper 2 floors of the structure. And the third case study was a building constructed in 1975, 5 stories tall in Pittsburgh, Pennsylvania, also a reinforced concrete structural frame, and in this particular instance, clad with limestone panels. This ended up being a much more complicated structural behavior issue, resulting in the cracking that you see exhibited in some of the panels that we found, and in this particular instance, a panel that was about ready to fall from the ground with a fragment that had broken loose. These are some of the original architectural drawings showing the system of how the panels were supported by a strong back truss system that was anchored to the concrete frame. This illustrates what we believe was the structural behavior of the cantilevered system. As the cantilevered structure deflected, it dragged the panels along with it, resulting in forces being applied to different parts of the system as it was deflecting that eventually created the distress that was observed. This shows the repair approach that we took for this building, replacing the fractured portion of stone with a new stone that was anchored to the structural steel behind it. Thank you for your attention.